Okay, hello. So essentially today we're going to be talking about optimization in data science and just go over a few of the common optimization methods and like just generally introduce it. So now what is optimization and why do we care essentially? So now Oxford Dictionary describes it as the action of taking the best or most effective use of a situation or resource. In data science, it's our way or our method of improving our models iteratively generally to either minimize a loss function or maximize a score such as accuracy or AUC. AUC is area under curve where we try and get the highest benefit out of our model. Specifically for loss, we can look at scores such as hinge loss, root mean square error, or our L2 loss to minimize to get the best out of our model. And everything we do after we have our data and we have chosen a model to use is essentially optimization for data science. We are trying to do the best we can with the model and data we have on hand, be this cutting down on features, improving them, and choosing the right feature and so forth to get a better accuracy score or better predictions in the end. So yeah, just general. Now, difficulties of optimization in general. Even though optimization often tries finding a specific minima, like we have a local minima right here, it might not be the best minima on hand. We need to choose methods that find a more appropriate value or an appropriate optimization score. And we also need to define constraints for our optimization problem. For example, in some cases, specifically optimizing only on the root mean square error is not ideal because while maximizing or optimizing for root mean square is great, if we only look is not great because if we completely minimize root mean square on our training data, it means we've overfit our data and it won't often perform well on testing data. So looking at the various methods of optimization, we're going to start off with gradient descent. This works by optimizing the gradient of our loss function or gradient of our score function. In the case of optimizing on the gradient of the loss function, we have a really small change in a coefficient in a model, and we see how it affects our function. Like here I focus on the loss function, but this can also be done with a scoring function. In the case of the loss function, we take a step down along with the gradient to reach a minima. In the case of a scoring function, you would take a step upwards along the gradient to reach a maxima. Generally, as you take more steps in this situation, you tend to take the size of your step tends to become smaller and smaller, which prevents you from stepping over a minima. Though the step size and reduction of step size is another optimization problem within itself. So you do actually reach a ideal minimum. This is just an example where we are taking step sizes to reach a local minimum. Ideally, as you can see in the leftmost case, you start with a decent step size and your step size keeps getting smaller and smaller till you reach a minimum. And it takes you about 24 steps. Ahead, you have a really large initial step size, but then it realizes the gradient at the next step size is not that large. So it takes a smaller step and you reach your local minima within 8 iterations. At the third step, you can see initial step size is way too big. While it still works, it is not ideal at all because you're just bouncing, you're crossing your minima each time you take a step and it's not efficient. And on the right-hand side, same issue. Your step size is huge. You're not reducing your step size ideally enough, and you keep zigzagging over the minima. While you do eventually reach it, it is not ideal.
Which one would you say is the most ideal?
Number two. Number two easily is the most ideal. Now, evolutionary algorithms. So these essentially work by taking the idea of survival of the fittest, essentially. They're an unsupervised learning alternative to neural networks. And essentially what happens is you generate a a bunch of solutions at once randomly. You have no idea about how good the solutions are going to be when you generate them. You randomize all the weights and so forth. And then each of your solutions are evaluated using a fitness function. Based on that fitness function, you select the most ideal solutions as long as they pass a certain threshold. And then from those solutions, you identify values or parameters that are considered ideal, and you merge them with other good solutions to produce the next generation of new solutions. After you've generated this next generation of new solutions, you introduce random mutations into these solutions to try and possibly find better conditions. And once you've done this, you have a second generation of values on which you can continue this process, and you can keep doing so until you reach a termination condition or you get a model that has passed the threshold of goodness, which you're comfortable using. This can just be expressed better in terms of flowchart. You initialize your model, you get a bunch of solutions that may or may not be good. You select the best solutions you want. You perform a crossover of attributes or properties between the solutions. You introduce random mutations into your new solutions, and then you select the best ones again. And you keep doing so until you reach a termination condition once you have a really good solution. And then the third model and last one we'll be talking about today is simulated annealing. It's a probabilistic technique of approximating a global optimum for a given function. This is specifically used in situations where you need to find the best possible weight area rather than a precise minima or maxima. This works in a manner similar to gradient descent, except rather than looking for a slope, you look at an area at once, and you select a point within that area at random. If that point has a better value than your current point, you can consider it immediately. If it doesn't have a better value, it takes into account the probabilistic function to consider whether or not you're okay using a worse value currently as the process continues. As you take more steps as time goes on, the chance that the probabilistic function chooses a worse value goes down, and the area that is considered for the neighbors also goes down. Eventually, this process forces the model to converge towards a global maxima or minima, and that process is shown here probably. Just give it a second. This started off in the middle, but here. So it randomly keeps going across a wide area. It sticks to points or sticks towards better points generally. And as time goes on, the temperature, so-called of the simulated annealing, goes down. It just focuses on the best global maxima. Any questions for now? We will be going over these methods later along with the code, but any general questions?
I'm going to show you how to implement all of these yourself in code and also kind of help explain like the reasoning behind some of these. So first, we're going to load in, our libraries as usual, and I'm just going to define some functions we're going to use. So first, I'm setting up a problem for us. So we have this data and we want to fit a line to it. We're going to use some linear regression, which we'll get into next time, but just think about like, okay, so we have this data, how do we, fit this? So first, we're just gonna pick some random parameters. We have the classic linear equation, y equals mx plus b. Let's just pick a random m and b and see where we get. So this was actually surprisingly good for just, picking out random numbers. It's definitely not the best, but, we just took a shot in the dark. But let's see how to actually optimize this. So in the beginning, we said that every problem is an optimization problem. So everything you're doing, like every model in data science, you're going to either be minimizing error or maximizing accuracy. And to show this, I just wanted to show like keeping B fixed in our equation, but varying M and seeing how this affects our error. So if we do that and we plot it, we can see we generate this curve, which this is usually a loss or a likelihood space, depending on like the literature you're reading, where the loss space is like how you vary your parameters and how the error responds. So here we varied our value of M, and then we plot that against how it changed the error. So you can see that there's a way to minimize the error in our fit by finding the ideal value of M. And this is a common thing across like all algorithms. You're basically just, searching your model space, your like model's weight space, or it's like parameter space, trying to minimize or maximize the error. So let's go over a way where we can, deterministically minimize our parameters, to fit the minimum error here. So as we went over, we are going to use gradient descent as our first model or first optimizer. And as you remember, probably from Calc 1, you took derivatives, and before they taught you like the really easy way to take a derivative where you just, subtract the exponent and all that. They made you do it by hand first, which the like idealized derivative here is like taking an infinitesimal step from your current step and measuring the rate of change. But we're working in the area of computing, not math now. So we have to actually have a discrete type of, value there. So what we're going to do is we're just going to pick a random point, x naught. So this is going to pick a random m, right, or b in our equation. Then we're going to take some small step away from it. Let's say like 0.1, 0.001. And then we're going to calculate where those evaluate in our loss space, and then see the rate of change between x naught and x naught plus h, and then divide it over h. Because we're really just taking like a local slope on our loss function to see how changing m that way worked. And it's a really neat optimizer because you don't need to know the global behavior of the function. You just need to know if that step gets you lower or higher. Like one of the best analogies I heard for like gradient descent is like, let's say you're trying to like climb up a hill, but you have a blindfold on, and you're like, you're searching, you're taking steps around, like, okay, I don't know what the hill looks like, but if I take this step, then I get to go up the hill. Okay, so that's a good step. We're going to go up. But also, if you find the opposite direction, like, okay, this step makes me go down the hill, to go the opposite direction. So you need to actually see anything. You just need to know what the next step and your current step give you. So what we can do is we can define a numeric gradient, which is just, I did this, but in code. So I'm taking, let me zoom in. I have some type of likelihood function, and I have some x2 and x1, where x2 is going to be a distance h away from x1. And I'm literally just following this formula. And then I just defined a simple likelihood for us for now as just x squared, just a simple, parabolic arc thing. And we're going to run gradient descent on this. So what we're doing is we're starting with some random x value and then stepping a random, or not random, but a small h away from that x value. Then we're calculating the slope between the error value we get from that m and the next m, and then determining which direction that slope is going. And we want to go down the slope or follow the negative gradient. And when we do that, we see that our optimizer is optimizing. If we let it run for more, it would find 0. But you see here, we started here, and then we took a random step h. So let's say h is this direction. We calculated the slope here, and like, okay, that's a positive slope. So let's go the other direction. Let's say our next step h was down, and like, okay, that's still going down. So we can follow that. And we keep, following basically the direction of like our steps, or the opposite direction if we're accidentally stepping up, until we find our way down the middle, or we're just kind of, taking steps down that hill, reaching out and figuring out, okay, which way is, down, but, in a math sense. So we call it derivatives instead of just a slope. So now we can see that this example is going to perfectly map onto our regression, right? Because we just proved that our regression is just an optimization problem for M and B. And so this shape and this shape are the same thing. We can use the same algorithm, but to solve a different problem. So for here, I defined some functions, which was kind of like a regression likelihood, which the regression likelihood is just say, hey, pick my M and my B, and then make predictions for, my line, and then find the mean squared error of my y and y predicted. And that error function defines my likelihood space. And then I take the gradient the exact same way I did for the thing above, where I first take the error of, my original step, and then the error of my next step, and then find the difference between them. And I do that with both M and B because we're trying to minimize two parameters. So now we can apply this same gradient descent in this loop. All it's doing is, hey, get my gradient. Hey, once I have my gradient, step in the opposite direction times some type of step size that we're defining, and then basically add that step size to our current M and current B, and then define the next M as our current M plus some type of small step. And we do that over and over. And look at that, it fit our data because all we did was minimize our error space. And if we look at how it did this kind of over time, we can see it started out with a really bad guess, and then it's converging up to the optimal line as we, step kind of into lower and lower values of error until it finds that minimum. And that's kind of that is our best fit. So that's how gradient descent works. Does anyone have any questions on how I did this or how you would implement it yourself? Yes. Yes. So why did I use like a numeric gradient than an analytical one? Because you might not always have a function that's differentiable. So here I'm doing simple examples, like I'm using like a simple parabola, and I know that, we can differentiate x squared, right? But if you, one, don't know what your space looks like, or two, even if you do know what your space looks like, it might not be differentiable. So you can always take a numeric gradient. You can't always take an analytical gradient. Yeah, thank you. So the next thing we're going to go over is the genetic algorithm. So like, as we said, a genetic algorithm follows natural selection essentially. So like here in this diagram, we have, some species or some member of the species. And then when it reproduces, it sets off variations. So like here, this is like the same as before. This is a little bit different. This is a little bit different. But, this member of the species gets axed. Like it has a bad mutation. It doesn't survive, but the other two survive. And as we go down, it's basically, survival of the fittest. So the ones with the, best mutations, or what we're going to translate into is the lowest error, will survive, and then it will get to reproduce. Or in our case, we will take that, lowest error term and use it as a seed value to create the next generation, which is just that seed value plus some variation. So first, we're going to generate a random population. So here, again, we're doing our linear regression. So we have M and B. So here, like I've defined a population of M and B, and I've defined a corresponding error, right? So here, let's see which has the lowest error. It looks like the first, let's say, member of our population of M and B has the lowest error, right? So because we know that the first index here is giving us a lower, or that's like the most fit out of our population, we're going to take these two parameters to seed the next generation because it's the fittest. And so what we can do is say, hey, the best line we can fit for this generation is going to be the kind of minimum error terms that, or the terms that give us the minimum error for M and B of the last generation. And then we do that and we can fit it. So that's pretty good already, where we just generated a population and picked the best set of parameters. But we can do better than this. We can run this again. So what I'm doing here is I'm taking M and B, and let me zoom in a little bit for you guys if I can. Yeah, there we go. So I'm taking M and B and I'm adding a random normal step. So just a step from like a Gaussian. And so I'm saying, okay, this is the best thing I have. Let's add random variations onto it until I get 10 things that are like similar to it, but with slight variations, or we can call them mutations, kind of keeping up with the genetic thing. And then once I run this, I can do the same thing. Now I have a population that looks like the best thing that I had before with random mutations. Now I see which one of those is the fittest. We can fit our best line. And this is already pretty good, but we can see it's already getting better here. So even after just 2 generations, we're getting a really good fit to this line. A really good thing about evolutionary algorithms is they're super parallelizable, or you can run like a bunch of different parameters at once. Like you can multi-thread the problem super well. And if you have like a low real time, but high like computational resource, you can go with genetic algorithms and like run like let's say you're trying to find the parameters to optimize your model and it has like 1,000 weights to it. Well, you can also like run a generation of like 1,000 agents or like 1,000 members, and that'll get you like, your best weights after a couple generations. So I really like genetic algorithms because they can be really time efficient if you have the computational resources. So let's do this same process where we start out with some random member, find the fittest member, use that fittest member to create a new population, then find the fittest member of that, but just do it in a loop. So here you call them generations. So I said here, do this for 25 generations and minimize the error for me. So here I run it, right? The first generation didn't do so well because that's basically guessing still. But as we're taking the fittest member of each generation and having it populate the next one, we're minimizing our error, and we start to converge towards some type of minimum, which looks to be like around 3.4-ish. And then we can do this and say like, hey, we fit a really good line. And all we did was we minimized the error with our, generations of parameters. So our next optimizer is simulated annealing. And I really like this one because it's actually modeled off of a physical process. Like we used a real engineering physics thing that happens, and then we built computation off of it. So that pleases my physics heart. Where the process of annealing is when you take metal and you heat it up, and then you let it cool slowly. And what that does is basically when you have a hot metal, the atoms inside of it are like very chaotic and they're like moving around. But as they cool down, they start to settle down. And once they end up settling, they settle in like the most like tightly packed configuration. And it's a way to strengthen metal. So they use annealing on like to refine metal that's been under stress because there could be like micro fractures in it. So you heat it up and like cool down, and then the fractures get filled in, or just to strengthen a piece of metal before you put it into something. And the computational thing to do is like exactly like this, where we have some type of, loss space. And it's a weird analogy, but the best way I can think about this is you have your loss space and you like pour a bunch of bouncy balls into it. And those balls are, bouncing around the loss space. And over time, their bounces are getting smaller and smaller, and eventually they'll settle into some minimum. And once you have that, you can pick the ball that's, in the lowest minimum and say, hey, that's a good approximation of our global maxima. Hopefully it is our global maxima. So in the, the computational model, we're trying to just, recreate what happens in the physical process. And I think that's cool. So for our simulated annealing, I'm going to define kind of like a toy likelihood space. I'm going to define it kind of more complicated than just parabola, because if it was just a single arc, it would be way too easy, and this would be an overkill of an algorithm. Which, by the way, that reminds me of a question. Do you think gradient descent would work on this? Yeah. Yes. It would work, but only to an extent, because it can only follow the negative gradient. So if you run gradient descent and you start here and you get here, it can never get out of there because it would never like climb up if it's trying to minimize. There are ways to get past that. There's like stochastic gradient descent, right? And there's also like Monte Carlo methods where you can like roll a random number to like accept like a worse likelihood in hopes of like finding a better one later. But we'll get into that in another lecture. I think we have Monte Carlo methods planned for next semester. Actually, that's like a whole host of algorithms that use randomness to kind of get out of sticky situations like this. But simulated annealing is really good because we're going to have a bunch of agents in here, and they're all going to kind of bounce around the space. And we talked about the temperature. So, you know, in real life, the temperature determines how much the like atoms move inside of the material. But in the simulation, the temperature is like the step size that each agent gets. So let's say we have a high temperature to start with. So each agent gets to take steps, and they're like really big steps. But as we saw before, if you keep taking really big steps, you're going to dance around your minimum value. You're going to like, you know, go here, and go here, but you're never actually going to settle into it. So as we keep taking steps, we lower the temperature or we lower our step size so we can actually settle into here. So first, we're going to, okay, this is actually a little too good. Someone already found the minimum by, you know, happened. Here, this is a better one because no one's starting out at the minimum. So we have a bunch of agents inside of our likelihood space, and we're going to tell them, and we're all just going to give them instructions. Take random steps, and if you end up in a lower place than you were, stay there. If not, go back to the last place you're at until we tell you to take another random step. So we're going to do this once. With the temperature, I'm setting at 1. So this is a pretty big step size for our space because there's kind of like from -10 to 10. So we're going to let them step 1. And just with one step, we can already see that they're doing better. Like this guy, even though he doesn't know it yet, but he's heading towards a local minima, but he did follow instructions. He is going down the hill trying to find the lowest value. And kind of the strength of simulated annealing, or where it's used the most, is when you have likelihood spaces like this, where you have many local minima, and also it's a really good algorithm to use if you have a very high dimensional space as well. And so we're going to do the same thing. We're going to say, hey, everyone, you get to take a step and hopefully find a lower place. If you don't take that step. But every iteration, we're going to lower the temperature and make them take a smaller step until they, you know, settle somewhere. So we're going to do this. And we can take, they did a little bit too well. This is what happened, but it did find the minima, but it only took one step. So one happened to take the right step directly at 0. Let's run this again. Maybe we can get it better. Yeah, or this took one step. Yeah, maybe we're gonna cut down, because I tried to plan it out so this wouldn't happen. But let's see what happens here. No, or this one didn't even make it. This one doesn't have enough agents. There wasn't anyone to step into the middle. So these are things to consider if you're going to use a simulated annealing. I think these usually use like hundreds to thousands of these little agents, and usually in parallel. So you put, you know, each of these guys on a thread and have them step and kind of like go down themselves. But yeah, let me just, okay, and what happened here? I mean, someone found it. Okay, to 0, but they didn't step down. Okay, this one was better. Yeah, so eventually someone found it, because it looks like they got stuck at 0 because the step was too high, right? So they made it to 0, and then when they're stepping, they like ended up here, or they ended up here, and it took what 4 iterations for the temperature to lower down enough that they could actually take the step to the actual minimum than getting stuck at 0. And yeah, so these are the basic optimization methods that are kind of behind all of your models. So whatever you're doing, if you're doing regression, classification, or clustering, all that's doing is lowering or like maximizing some value. So you're either going to lower or minimize your error, maximize your accuracy, whatever you're doing. So I hope this gives you a basic overview of what's happening behind the curtains, you know, when you're using sklearn or whatever, what have you. it's really just using one of these in an intelligent way. So does anyone have any questions or want to ask about other optimization methods? Okay. We're wrapping up early. I think we're getting more and more tired as the semesters go on. I can't lecture as long, but
Just throwing this out, there's an interesting website. I'm not sure if it's an op, it used to be called